Looks like we're live on X, YouTube, and Twitch. Getting a little bit better at this whole complex setup I got going on here. Alright, let me close out of that. Oh, that's cool. Alright, let's refresh that, and that. Chat is disabled for this live stream. I don't think that's the case. Pop out chat. Okay, I need to do that. Close that one out. Is there something wrong with Twitch? Huh. Interesting. Okay, seems like it's working. All right. Let's see here. ZeroXCC.io. So I last night after the stream went and set up Cloudflare pages and my domain and everything. Got TLS going. Super simple. Cloudflare makes it really easy on you. So I got a basic website going. So now when I push to the master branch of that repo, it'll publish the updates up here. And this is the post that I worked on last night. So yeah, that's working. If we go to Twitch here, I have that schedule published here. Let's go down here. Yeah, 1 to 5. So I was running a little bit late today, an hour late, because I got to the gym late and I had a accountability pod meeting this morning. So everything just kind of got backed up. But I'm here now and I am going to be working on the parallel computing course problem 2. I believe there's 6 problems in here, so I want to make some progress on those today. So yeah, let's start on program 2 since we're completely done with program 1. Take a look at a function clamped example serial and program 2 vector intrinsics main.cpp. So prog 2, let's look in here. Let's just open up the make file. I always like looking at the make file first. Make file, there we go. So we got our clean. I guess it's if I just run make on here and do git status, you can see echo these guys. Actually, I should probably just do a vim.get ignore, paste them in here, and put them on their own lines here. Oops. And there we go. And then git add that guy. Okay. So we got 2 object files and a binary. Which if we open up the make file again, these are our object files. We just do gcc on them. We include a bunch of CPP and header files for intrinsics and logger. And then this is intrinsics and loggers as well. I wonder why they both need each other. That seems odd. And this needs both of those object files, and the main CPP includes common, which probably for logger. No loggers here. So I don't know why it needs common. I wonder if it'll build without that. Let's test it out. Make clean, make. Yeah, it builds without it. So they just had it in there for funsies. We're not going to do that though. Okay, let's look at main.cpp. Good place to start here. Doesn't seem like we need this algorithm thing. But sometimes you do need it, and Clang D is just kind of freaking out. So we got our 4 declarations here. We're pulling in these 2 local header files along with that. Let me make clean and make. Yeah, we don't need that. Okay. Exponent max, then we declare a logger. That's a global variable, not a function. Then before declare all of these, that's not initialized. We got a main. Let's go down. Usage, init value, verify results. Abs vector. So it's doing a bunch of intrinsic stuff. Clamped x serial, clamped x vector, array sum serial, array sum vector. So I guess we're going to implement the vector thing here. These two things. Okay, so, and these are just all four declarations for all of these same things that we have down below, so that our main can call into them, I guess, without the main being at the bottom. I actually don't like it when projects do that. I'd rather just have the main at the bottom. Anyways, we have N16, print log is equal to false, parse command line options. So we have long options, 1, 2, 3, 4 elements of this array, and size has arg s, log has arg l, help question mark, and then a null. It's not a null, but it's a 0 value at the end to terminate it, probably. Alright, and then we got here, so this is called getUpLong. I'm not familiar with getUpLong. Which is part of getup. And we say, hey, we want the S, the colon L, and the question mark. Here's the long ops. And that just kind of goes in and if we say -L, we get the log. Everything else, we get usage. argv 0, pretty typical. S is assigning n to be equal to the parsing of it. Alright, makes sense. Here we just say, hey, I got float values is a new. This is C++ syntax. So I'm actually not. I took a course in my undergrad where I spent some time learning C++. I wrote like my projects for that class in C++, obviously. They're fairly complex, not super insanely complex projects. I forget what I was using at the time, but I was like using some crappy IDE, I believe. Maybe I was using them, I forget. But I remember using some crappy, I was using some crappy IDE because I had it built for Windows, and that's the only way I could figure out how to do it at the time. Anyways, my experience with C++ is very limited. I have on the schedule this year to read 2 books on C++. So I will be skilling up on C++, but for the time being, I have to rely on my C knowledge in understanding this and my small amount of knowledge in C++. So new is a keyword that will dynamically allocate the value on the heap, basically. And I think something like values probably doesn't need to be garbage collected. It's a pointer. We get past the pointer into a bunch of functions here, and then we call delete, or we use the delete array keyword. Again, I wasn't familiar with that. I would think this would be sufficient, just doing delete, but I guess maybe that's if you have an array, I guess you have to do a delete array syntax. Okay, so this plus vector width, interesting. N plus vector width, is that a constant? I don't remember seeing that declared at the top here. So how is that building? Where do they assign vector width? Is that something that is in a header file somewhere? It looks like it might be. Let's go ahead and write out and grep for vector width. Sorry, vector. Okay, so this is where they pound defined it in the CS149 intrinsic.h. So there's a header file there. The pound defines it as 4. which is interesting because I think I can actually fit more than that. So we'll need to update that. And then we got logger here. Just logging it out. Okay. Lots of intrinsic stuff here using it. I don't see any assignments outside of the header file. Sorry, it's a preprocessor macro, so it wouldn't be an assignment, but I don't see any redefinition of it, I should say. Okay, so let's jump over to the header file real quick, and I think I'm going to do 8 here because I have AVX 512, and if we go back over here, the first use of that is with float. And if I just bust open here Clang REPL, and I say include printf, and here we'll say %LD new line, and we'll say size of, and then in here we'll say float. So that's 4. A double would be 8. Makes sense. So we have 4 bytes, and we have AVX 512, which is literally 512 bytes. So if we do something like 512 divided by 4, we're going to get 128. That's the width that we have for floats. Seems much... Yeah, it seems much larger than I would have thought. No, it's 512 bits, not 512 bytes. Yeah. That makes sense, 16. So you can fit 16 with AVX 512. So we'll redefine that to be 16, which is in the header file here, to be 16. So what is the vector width on AVX 512 for float 32-bit value? $16 exactly. Okay. Alright, I'm not going to spend any more time there. What is this expected expression? Okay. Make? Oh, we got lots of errors on this one now. All in this one file? Wow. Okay, we're going to have to pipe that into head because I can't read all that. Oh, because I did an equals like a moron. Alright, there we go. Make. Alright, so we're still building. Let's go back here. Alright, so our vector width is now 16. We have values, exponents, output, and gold. I'm not sure what all that is. We then call this init value, passing in the pointers and this n value, which is, so we, should this be multiplication? We say, hey, n is 16 plus the vector width. Wouldn't it be times the vector width? Or divided by the vector width? I don't understand why you're adding the vector width. I'm trying to understand why you would do that. They defined it as 4, so it'd be 20 in their case. Int is also a 32-bit value. Okay. So they add the vector width onto here. The only reason you do an add instead of a multiply or a divide would be is if only one element, the last element. But even that you wouldn't even do a plus because yeah, I'm not sure about this. But anyways, this thing just puts random values, it looks like. I'm not familiar with static cast float rand, but I'm sure multiplying that by 4 and then divide it by rand max and then adding 1 or -1 to it is going to give it a random value. Same thing here. So that'll bound it to the exponent max, which is 10 to the power of 10. Outputs and gold is 0. Okay. So we're still in the main here. Clamped exponent serial. So we do value exponents gold n. So gold is like the golden file type pattern where you say I'm going to run the serial process on this gold output and then I'll compare the gold to what I generated with my vector, make sure that they're the same. Accepts an array of values and an array of exponents. For each element, compute values I, exponents I, and clamp value to 9. Still result in output. So this goes to every element, not including the stuff, the n plus vector size or whatever. Oh, maybe they do the additional vector at the end just to make sure that you have space to perform the vector operation, because you're doing it on a certain, that would make sense. So you're doing the vector operation on, say, like an 8 wide array. Well, what if you only have 4 values? You still need to provide it an 8 wide array. And so the values at the end of the array, the 4 values at the end of the array, need to be reserved, like padding bytes, so you can perform the same operations on them and it doesn't corrupt data elsewhere. Because an array doesn't get aligned, or at least an array of characters doesn't get aligned. So I guess they're not concerned about alignment. But if you have like 512 bits that you, let's see, 64, 128, 256, 512, so that's 4, 32, what is 512 divided by 8, is it 64? Okay, it's 64. Because 128, 256, yeah, because you have 3 bits. Yep, okay. So 64 bytes is the size of AVX 512, which would be a cache line. But it's not going to be guaranteed to be a single cache line because they don't align the whole array. Mod 512. Or I guess this would be a register, because the 512 AVX 512 register. So when I'm loading data into the register, I need to make sure that when it's stored in memory, it is 512 byte aligned. So anyways, I think they add on that additional additional vector width to n when they're allocating the array and when they're initializing it apparently as well. They add that on so that you're not clobbering
other areas of memory when you're performing vector operations if they're not, if all the values aren't in that vector, basically. If you only have 4 values and you're performing it on an 8 wide, or say you have like 12 values and you're doing 8 wide, the first 8 perform fine. You go to the second set, which is only 4. Now you need space for an extra 4 that you just throw away, but it can't be actual memory values that are in use. So that's why they do that. All right, let's go in and finish reading this. So we're just ranging over n. We read the value, we read the exponent. We say, hey, if the exponent is 0, then output's pretty easy to compute. Otherwise, we take x and we store it in the result. And then we say y minus 1 is going to be the count. While count is greater than 0, we multiply the result times. So the minus 1 here is because we already have 1x stored in the result. Every time we multiply the result times x again, we decrement count. And when it's greater than 0, we just run it until it's equal to 0, which means that we don't have any more exponent left. And if the result is greater than 9, then we just set it equal to 9, which is the clamped aspect of it, and then we just assign to the output. So pretty straightforward. Yep, that's what it says on the tin. So then we got this clamped exponent vector, which has the same exact prototype, except we're intended to do this using vector operations, intrinsics, which I have 0 experience with. Not 0, very little experience with. Returns the sum of all elements and values. So this one, you get the values and how many elements, and it just ranges over the values and increments sum of the value, and then returns sum at the end. So this one's going to be hard to beat, especially with a contiguous array, as far as runtime, doing it serially versus doing it with vectors, because CPUs are really good at just like running through memory in order and like doing these aggregations on a single register. That's like really pretty performant. And the vectors, what we're going to have to do is compute the sum of a range of values, the vector that's in memory, with an existing vector, if that makes sense. So we have our accumulator vector, which is 512 wide. And then we range over the values. Every 512, we're incrementing the accumulators in that vector register. And at the end, we have to sum all those elements of that register up into a single register and return it. A single like general purpose register. But we do have the problem where that memory needs to be 0 initialized if there isn't a value, so that when it gets summed, it's 0. And that's why up here, when we initialized the values, oh no, they're all random here. Let's see, is that what we're using? Array sum serial. Yeah, we use this values thing. The values was the first thing. So that means they're all random. Well, that's not good. That means that we could be adding elements to the output, like this vector with those elements don't need to be in the output. So we need to be able to mask them off somehow. So that's probably going to be part of the program, is to figure out how to do masking. Otherwise, if we're just blindly summing into a single 512 register, we're going to be summing in those extra values as well if it's not a evenly spaced vector. Like if we have 12 values and working on eight wide, then we got problems. Okay. Returns the sum of all elements and values. You can assume that n is multiple of okay. So we don't have to, so they allow us to have that assumption here. Whereas up here, I'm assuming they don't want us to have that assumption. How would we do the clamped exponent vector without that assumption? Values exponent output. Let's look at the init of the values. Back up here. Exponent output. Okay. Huh. So probably going to need to read these into a register, the values. And then, okay. The problem with this is that this is like variable based on the value of the exponent. So you can't just do one loop for all elements of the vector. That's going to be tricky. But in principle, I think it's going to be a load, store obviously here, and here. And then this is going to be the tricky part of this while here. Hopefully it's like an operation that just says, hey, grab this byte out of memory, or this vector out of memory, and just like raise the value that's in their register to this exponent. And then we don't have to worry about it. Well, we will have to worry about... No, I don't think we have to worry. We don't have to worry about the extra values, the vector width values, because who cares if we compute the results? Like, we're just not going to use them. They don't impact the end result, whereas this one, it actually does impact the end result if we compute it. I think we can get we could implement it where we don't make this assumption, but that'd be a little bit more work. But I think you can do it. Well, I know you can do it. Okay, so I just want to get a feel for all these different functions and what we're going to be implementing here. So that's clamped exponent, clamped vector, erase sum serial, and erase sum vector. So obviously we're going to be implementing the vector stuff. There's an abs serial and an abs vector. Verify results. So let's read over abs serial. Computes the absolute value of all elements in the input array. Values, stores the result in the output. So it performs an abs on the array, basically. And this one just iterates over every element of the array, reads the value of the array into register or local. If it's less than 0, then we assign it to output. Okay, so we're putting it to output. So we're doing a copy regardless. We're doing a load and a store. Versus, well, I guess I should say we're making copies. We're loading from values and we're storing into output, but
it's not in place. I'll say that. It's not an abs in place. It does not mutate values. All right, implementation of abs serial above, but it is vectorized using CS149 intrinsics. Oh, they have their own freaking intrinsic crap. I don't like that. Means that for me to use the AVX 512, I'm gonna have to like probably gonna have to mess with stuff here. They probably did this to trim things down because there's so many fucking intrinsics. It's like very overwhelming. Alright, we're not going to dive into intrinsic definitions yet. But suffice to say, we create a float vector for x and result, and 0, where we call vset float 0. So just 0 initializes the floats. And then here we're dealing with masks. So it's good that we have an example for masks. Note to take a careful look at this loop indexing. Note, take a careful look at this loop indexing. This example code is not guaranteed to work when n mod vector width is not equal to 0. Why is that the case? So we go from I 0, I is less than n, I plus equals vector width every time. So I think that's fine. Take a careful look at this loop indexing. This example code is not guaranteed to work when n mod vector width is not equal to 0. But we're guaranteed to have added the vector width. Oh, I guess what he's getting at here is that, like, we don't know what you've given us. Like, it could be initialized anyway. The fact that I know that it was initialized by adding the vector width to n in the initialization process means that I know that this isn't going to be an issue when n mod vector width is not equal to 0. But if you passed me an arbitrary float values and an arbitrary n, and it wasn't initialized properly, with the right amount of spacing at the end, padding, then it could be an issue. But let's read through the code just to make sure that's the only thing that's going on here. So all ones, so we just mask all zeros, mask is negative. If we say this is using them, yeah, these masks could probably be pulled out and initialized up here because I don't see them getting mutated. Yeah. Okay. Load vector of values from contiguous memory addresses. So we say, hey, vload into x. The source is going to be values plus I. And we're going to mask, we're going to just read everything. And then set mask according to predicate. So we say, hey, VLT float. So we got passing a mask all 0 x, mask is negative. I don't know what that does. I mean, it says set mask according to predicate. Which mask? Mask all 0. I guess 0 is not a mask, but it could be mask all, mask is negative, mask is not negative. I'm guessing it's mask is negative. So mask is negative is getting assigned to. But mask all doesn't get mutated, right? Execute instruction using mask if clause. Okay. Less than, vector less than 0. That's what's going on here. So this is a vector load, this is a vector less than. So it's saying if the value at position x for the element of the vector is less than 0, then it becomes part of the mask is negative. So that's why it's like a condition in the comment there. And then here we say, hey, subtract v sub from 0. Okay, so we're saying, okay, subtract from 0 the value in x if it's negative, which will make it absolute and store in result. So now result was the result initialized to the values in x? No. So that takes care of the negative values being absed. But now we got a copy of the positive values as well. So we just negate the is negative mask. And now we say, hey, load into the result the values where we're operating at according to this mask, so only the positive values, and then we store everything back in memory. Okay, so this is pretty straightforward. Cool. And the last thing in here was this thing called verify results, which gives us values, exponents, output, and gold, and n, and does a bunch of checks probably. So it says, hey, incorrect is -1, epsilon is 0, 0, 0, 0, 1 for range over all the elements, including the padding at the end. And then we say, hey, if absolute value of the output and the gold is greater than some very small value, so we're making sure that it's within a certain tolerance. Then we set incorrect and break. If incorrect is not equal to -1, if it's greater than or equal to n, then we have issues to the out of bound values. You have written to out of bound value. Otherwise, well, that's just a one-off thing there. Then we say wrong calculation of value, incorrect. The value is equal to, and then we range over all the values in n and just print them out with no new lines. And then the exponent, we do the same thing. And then the output, we do the same thing. And then the gold, we do the same thing. So these are our inputs, and these are our outputs. And we compare the two, and we say, hey, if you got through
all of that without hitting an incorrect one. We say results match with the answer. Sure. Okay. So I fully understand everything that's going on in this file. Let's actually, I haven't read some of the main still. Let me go through and finish reading the main. So you call clamped. We're also going to be calling the abs. What about the other thing? So we have abs, we have clamped, but this array sum serial. Where's that being called that? Okay, in here. So clamped is up here. We do a verify result. And then we say if it passed or failed. And then we do the same thing for array sum here. Okay. What is this epsilon again? Okay, so that's similar to the verify result thing, but they're just doing it here instead. Because this single value is not an array. It's a little bit easier to do in line. So you say, hey, some gold minus some output, absolute value, it makes sure that it's less than epsilon times 2. Is this the only place we're using epsilon? It's different epsilon. I don't know why they just didn't put the constant value there, whatever. And then if it's not correct, then I go out failed, otherwise say passed. And that's if n mod vector width is equal to 0. Otherwise, you say you failed the assumption. Okay, so that takes care of the main. Logger I'm not terribly interested in, but obviously the intrinsic file is important. And this is 261 lines of code, intrinsic code, which I'm not tempted to read. But it's not more than the main. Yeah, I don't know if I want to just dive into this. So the mask is a vector of booleans. Interesting. The vector is... Okay, so they're doing some C++ templating here. So you can provide your own parametric type here. And that just becomes the array of vector width in the vector. Okay, and the mask is just that of bool. Float is float, int is in, that all makes sense. Why is this one declared as a struct? Like that, and this one is a pound define? Maybe because this thing is gonna pack them into a single numeric value instead of leaving them as separate characters for the bool. Maybe? I'm not sure. I don't really know C++ that well, so I'll have to just assume that's the case. Function definition. Return a mask initialized to 1 in the first n lanes and 0 in the others. These are all just function prototypes, which we can read the implementation of in our file. Okay. So this thing is pulling in the header and the header pulls in standard lib and math. I'm kind of curious what is actually, like, where the actual intrinsic instructions are. So this is just a serial. These look very serial to me. Like we're iterating over the array and we're applying the thing. I don't like this. This isn't actual intrinsics. Like, what is the point of doing all this if you're not going to use SIMD? Oops. Oh, maybe C++ is able to do auto vectorization on this stuff, so you don't have to do intrinsics. I mean, the compiler is probably smart enough to figure that out in these simple functions. What compiler flags did I have here? No optimization flags. It's just the basic -C. Okay. Well, I guess we could disassemble it. See what's going on if it's using intrinsics. So let's do an obj dump on the object code for it's capital D CSO. And I'm going to pipe that into less. And we're going to go to __ CS something. Yeah, here we go. We got some functions here. That's a mask. CS149. How about here? Oops, grab my marker. So, oops. These look very much like not SIMD operations. Yeah. It also looks like they are name mangled, which makes sense because it's C++. Yeah, I don't see any SIMD instructions here. Very much serial code. Okay. Well, I wonder if they're going to ask us to implement it using actual SIMD code instead of this pretend vector intrinsic thing. Because I'm not seeing this as SIMD. Like, let's pick out one function that we know should be SIMD in that header. Which would be what? I guess we already looked at count bits. Is there like an add? There's a move. There's a load. Yeah, the vector load. Let's do that. Vector load int. So let's quit out of that. And we'll do our obj dump again. And then we'll search for this function. I think that's the function, right? No. That's a bunch of mobs into a call. So I'm guessing that call target is going to be our actual implementation, maybe? Let's go back over to here. Look for that again. What does this do? It calls CS149 vload int. Vload of int. Why is this? Okay. So basically vload is templated out that way. Maybe vadd? Here we go. That one we should see a loop for. So let's quit out of that. Search for this. Vadd on int. Should we go back up here? I'm guessing it's going to be calling this int r11 vec. Is that a recursive call? Push mob sub mob. Call. Okay. Yeah, I mean, this is just like jumping to like 78 over here, jump less than, jump equal. This is a bunch of jumpy code. It's not SIMD code. I mean, I'm not fully precisely looking at like tracing through what this thing should do, but my vibe is that I'm just getting the vibe that it's not SIMD at all. All right, let's read the instructions. Maybe that'll illuminate us. I wanted to read the code first because I feel like I can't read the description until I have some understanding of what is in the code. So let's go ahead and read the description now. Vectorizing code using SIMD intrinsics 20 points. Take a look at the function clamped exponent serial. The clamped exponent function raises values I to the power given by exponent I for all elements of the input array and clamps the result values at 9.99. In program 2, your job is to vectorize this piece of code so it can be run on a machine with SIMD vector instructions. However, rather than craft an implementation using SC or AVX2 vector intrinsics that map onto real SIMD vector instructions on modern CPUs, to make things a little easier, we're going to ask you to implement your version using CS149's fake vector intrinsics defined in CS149 intrinsic H and CS4 intrinsic H. Library provides you with a set of vector instructions that operate on vector values and or vector masks. These functions don't translate to real CPU vector instructions. Instead, we simulate these operations for you in our library and provide feedback that makes for easier debugging. As an example of the CS149 intrinsics, a vectorized version of the abs function is given in main CPP. This example contains some basic vector loads and stores and manipulates mask registers. Note that the abs example is only a simple example, and in fact, the code does not correctly handle all inputs. We'll figure out why. You may wish to read through all the comments and function definitions in the intrinsics to know what operations are available to you. Okay, do I want to do that right now, or do I want to continue reading? Let's continue reading. but I might want to read through that at some point. Here are a few hints to help you in your implementation. Every vector instruction is subject to an optional mask parameter. The mask parameter defines which lanes whose output is masked for this operation. A 0 in the mask indicates a lane is masked, and so its value will not be overwritten by the result of the vector operation. If no mask is specified in the operation, then no lanes are masked. Note that it's equivalent to providing a mask of all ones. Hint, your solution will need to use multiple mask registers and various mask operations provided in the library. Hint, use CS149 count bits function helpful in this problem. Consider what might happen if the total number of loop iterations is not a multiple of SIMD vector width. We suggest you test your code with exponent as 3. Hint, you might, so this is basically like I changed that value assuming we were going to use AVX 512, but considering this is just like pretend land, we're not actually using SIMD, I think I can change it back. So git diff on CSH. So up here we can change our vector width back to 4. So that goes back to 4. Cool. All right. Hint, you might find init1s helpful. Use exponent-L to print a log of executed vector instructions at the end. Use function add user log to add customized debug information in log. Feel free to add additional print log to help you debug. The output of the program will tell you if your implementation generates correct output. My neck is just killing me. I pulled a trap muscle on Friday last week. I don't know doing what. I've been doing trap exercises, but I don't think it was a trap exercise that pulled the muscle. And then today I had trap exercises scheduled, some shoulder shrugs, and I did lightweight just to warm up the tissue and to get some blood pumping through there to help it recover. But basically Friday, Saturday, and even into Sunday, it was like really painful. And I woke up this morning kind of in pain, but Saturday was probably the worst pain. It seemed like it was getting better, but I did like 80 pounds on each arm. That probably was too much. I mean, I was doing like the whole stack last week, so it was a lot less than I normally do. It's like one of those things, like, if you just keep on aggravating a minor injury like this, it's not going to heal and recover. But you also want to get blood into the area to help it heal and recover. So it's like, how much should you load it? But it might just be that my traps are fucked for this cycle. I need to talk to my coach about it tomorrow. All right. I'm getting kind of bored with like reading this stuff. To be honest. I'm going to grab some water because I'm getting hot too. And just think about this a little bit. So the goal here is to implement their exponent thing using their fake intrinsics, which seems like a very straightforward thing to do. I don't see the value in it though. Like, I wanted to actually use the SIMD intrinsics and not like have fake intrinsics. Like, what value does the fake intrinsics give you? I feel like sheltering your students from complexity does them a disservice. I feel like students need to be forced to just do the thing in a real situation. Because in the real world, when they're working, they're not going to be able to pretend like they have some like easy exit, easy option. But maybe just for the purposes of getting through all this crap, I do it. Do we actually use SIMD at some point? Let me rip grep for underscore mm. There's an mm free and an mm malloc. What are some common intrinsic functions in C for SIMD operations? Yeah, they all have, well, first of all, you're going to be including this. And we don't. And the only thing that we have here is underscore mm free and malloc. Which I don't even know if that is in multimedia. Let's go ahead and run this just to see it fail. Actually, I need to go back over here. There you go. Cool. All right, I'm gonna take a break here then to grab water, but I'll be right back.
Oh shit. Sorry, someone invited me out tonight and I totally forgot. Oh, God, my back. Oh, this is a really nice, helpful guide here. So it's multimedia, the width, so 128, 512, 256. So 64? Is there 64? Because I see things that don't have the width, like add PS. Is that 128 or is that 64? Um, Width is implied or explicit. Operation, and then type. PS is packed float. Why is it S? Single precision. Packed double precision. EPI packed integer 32. E, what does E mean? Generic integer vector I28 signed. Huh.
Oh, okay. So there is a scalar used with the SSE extensions, multimedia extensions. All right. And then what is E in EPI 32? What does SI 128 mean? Why? What is S in that context? Integer element. Packed integer. 32. What is E? Element. I don't understand that. Why EPI 32 versus just PI 32? I don't understand it. Packed single, packed double, scalar single, scalar double. These I'm very familiar with. That makes sense to me. So this is a scalar int 128. No, it's SIMD. I guess scalar has to be on the left-hand side of S or D. Otherwise it means SIMD. Integer 120-bit. Element type suffixes versus generic register class suffixes. You describe whole vector register type. So that'd be SIMD integer 128 up to 512. Yeah, so this thing is like, I don't really care how you interpret these bits. I'm just setting them all to 0. So there's nothing in this function that cares about how you interpret the bits. So operations that do care how you interpret the bits will have
element type suffices. Operations just care about what register you're dealing with. They'll have register class suffices. So S is going to be scalar or SIMD, depends on the context. P is always packed, integer, double. So it's scalar single, scalar double, pack single, pack double. And then element, packed, integer 32. And then SIMD, integer 128, vector. Okay, well, it doesn't take too long to figure that out. Okay, let's go ahead and close out of that, and we'll go back up here. So let's read the last, wait a minute, where am I at here? I need to go to this here. The output of the program will tell you whether implementation generates correct output. If there are incorrect results, the program will print the first one it finds and print out a table of function inputs and outputs. Your function's output is after output equals. It should match the result after gold equals. The program also prints out a list of statistics describing utilization of the CS149 fake vector units. You should consider the performance of your implementation to be the value total vector instructions. You can assume every CS149 fake vector instruction takes one cycle on the CS149 fake SIMD CPU. Vector utilization shows the percentage of vector lanes that are enabled. What you need to do, implement a vectorized version of clamped exponent serial in clamped exponent vector. Your implementation should work on any combination of input array size n and vector width. Run my exponent s 10,000 and sweep the vector width from 2, 4, 8, 6 to 16. Record the results in vector utilization. You do this by changing the pound defined vector width value in the header. Does the vector utilization increase, decrease, or stay the same as vector width changes? Y. Extra credit, implement a vectorized version of array sum serial in array sum vector. Your implementation may assume that vector width is a factor of the input size, array size n, whereas the serial implementation runs in O of n. Your implementation should aim for a runtime of n divided by vector width plus vector width, or even n divided by vector width plus log 2 of vector width. You may find the HADD and interleave operations useful. Okay, I think the next step for me then is to read the header, or read the actual implementation of CS149 intrinsic CPP. And given I don't know CPP, I'm going to struggle a little bit here, but it's fine. So init ones. What is this first? So we declare a mask, and we already determined this mask type is just a vector of bools. So we get that copied out of this. So value.
am I even streaming for? 'Cause I feel exhausted right now. I feel like I want to take a break from this. I've only been going for an hour and 20, and I already took a break. Yeah, I might just take a little nappy nap here. Yeah, I think I want to stop the stream and go take a nap because I feel exhausted. And then I'll come back to this fresh after my nap. I'll read over all their intrinsic operations to get a picture for what they're kind of getting at here, which is about 200 something lines, 260 lines. And then once I've digested all that, then I'll go through and implement the two things here based on their hints. They give a bunch of hints here. All right, I'm gonna go take a nap. All right, I'll be back in probably about an hour, maybe a little over an hour.